think Rakesh and I both are going to present. Rakesh is going to take care of civil. We need that one also. We don't need this one, right? Can you hear me? Oh, it's probably. Okay, okay.
Let's turn this off. Zoom decided to change some settings, so I like changing settings. Okay, it's live.
Okay.
And you can hear me also? No? Okay.
Can you hear me? Oh, so then
I'll introduce you and then you can take. All good? Okay, let's get started. So today we're going to have another lecture that covers some of the work that we have been doing in memory and storage system design. So far you've had lectures on memory robustness by Girai and accelerating genomics by John, right? Did we have that? No, we didn't have that. We had. Are we going to have that? We should have that also. Okay, next week. I reordered the concepts. Yeah. But you had memory-centric computing by Geraldo. And today Rahul is going to talk about machine learning driven memory and storage system design. But also Rakesh may actually jump in part of it. I'll let you guys decide how to do it. But you have the opportunity to hear from another person who's going to be graduating with his PhD soon in a few months on essentially this topic, or partially this topic, more than this topic. So you can ask him a lot of questions. And next week, we're going to talk about genomics, right? Okay, so I think this is a nice opportunity for everyone to see people who have either finished their PhDs recently or who are going to finish their PhDs very soon, like Geraldo and Rahul. Okay, Rahul.
Thanks a lot. Okay, so thanks, Onur, for the introduction. I think I'm audible, right? Everything is good. Okay. So as Onur said, like today we are going to discuss about machine learning driven memory and storage system design. So I'm going to introduce some key concepts that we have been working on the memory side, and then Rakesh is going to jump in to discuss on the storage side how machine learning can be used, and then yeah, we are going to see some examples of it. Okay, so with that said, so this is some brief background of ours. So I'm Rahul. That's Rakesh over there, who is my colleague, and we have. So that's the easiest way to reach out to us with this email address. If you have any questions regarding today's, let's say, lecture and all maybe some ideas that you want to discuss, feel free to drop us email over there. Okay, so our primary research interest lies in microarchitecture and memory storage system design, as we just discussed. So high performance memory storage subsystem design, including prefetchers, cache management, SSD management. And we are kind of exploring what we call the data-driven architectures, right? So, and then in the remaining part of the lecture, it's going to be hopefully clear more. What do we mean exactly by data-driven architectures? Machine learning assisted policies inside the processors, inside storage devices, to improve access latency, improve fairness, quality of service, and so on and so forth. Okay, so with that said, so that key the term that we used over data-driven architecture. So what exactly does that mean? So as we, at this point, I think it's completely evident from the previous lectures also that computing as it stands in today's time, it's heavily bottlenecked by the data. So be it from the large scale recommendation system, large language model that you have already, interacting from day-to-day life, graph tree processing, genome sequence mapping, which we are going to see in the next lecture also. Most importantly, data is often the critical performance and the energy bottleneck in today's computing systems. And this is not only true for, let's say, large scale systems that we are interacting with on, let's say, server scale, but even if you're on your mobile devices, right? Like, let's say, for example, Chrome, TensorFlow, that's executing in your mobile, as well as your video encoding, decoding codecs, right? So these applications are also in general heavily bottlenecked by data, and they are the main performance and energy bottleneck. And the same trend goes on. We have seen this picture in the last lecture also. I'm just flashing the same thing. Even let's say emerging workloads, like for example, genomic sequence analysis, we are going to see it in the next lecture also. There, the story is essentially same: data, and how exactly we can, access on data or process data more efficiently, more high performance way. So the axiom towards designing today's system and also the next generation system that we have is essentially this statement that an intelligent architecture should handle the data well. So, but then the architectures that we are seeing today, they are actually on the contrary side. So what do we mean by contrary? So these architectures are very terrible at dealing with the large scale of data, right? And so they are, most of the processor or most of the silicon real estate that we invest, they mainly store the data or move the data around from one hierarchy to the other hierarchy, as compared to compute on the data. And so this trend is what we are saying, that okay, today's architectures they are more processor centric as opposed to being data centric, and on which we have touched upon in the previous lecture, that how exactly we can re-envision systems on being data centric, making the computation closer to where the data resides rather than the vice versa, right? And we are also seeing that these architectures are terrible at taking vast amount of data and the metadata into considerations and learning from them. So as a result, they designed to make simple decisions and ignoring lots of data that they are getting generated on the fly. And as a result, what we are seeing is essentially that these architectures are mostly human design driven. Like, for example, what we design in your laptops, in your mobile processors, there are certain policies that we have designed as a human designer from the get-go, and no matter how long you have been using these mobile devices, how long you have been using your laptop, they're still taking the same decisions again and again, even though they are probably seeing, let's say, 5 years, 4 years worth of data, that how you are using your device, right? So there's definitely something not correct there. So that's what today's most lecture is going to be: how we can re-envision at least certain part of the processor to be from a human design driven decision making to a data driven decision making. And at the same time, these processors are also terrible at knowing or understanding the semantical characteristics of the data. So as a result, what happens is that they treat all types of data in the same way. And this is what we call that they're taking component aware decisions as opposed to taking data aware decisions. And we're not going to touch upon this part, but if you're interested, then definitely let us know, and we can discuss it like individually also. So this is what the corollary or the vision is for us. For intelligent machines, we want it to be data centric, data driven, as well as data aware. So the data centric part is what we have seen in the last lecture. Data driven part is what we are going to cover in today's lecture. So as I have already mentioned, what do we mean by data driven? That today's processes are mostly human driven. Humans are the ones that are designing the policies, and as a result, what our policies also reflect is our own set of limitations, right? So mostly these policies are going to be short-sighted, so they are very bad at anticipating the future, let's say, taking long-term taking actions which are going to benefit in the long term, rather than taking myopic actions having very short-sightedness in the future, right? So that's, and then there is very limited, if not anything, in the automatic data-driven learning in in these policies. And yeah, as I said, like there is no learning for whatsoever in many of the cases. So then that raises the question that can we design fundamentally more intelligent architecture which learns itself from the data that it sees, right? So the data that might be coming from the workloads that you are running, as well as the data that the processor itself is also generating, every sorts of data, metadata, we need ideally to learn from it and grow better from time to time. So that's the data-driven part. I'm not going to go too much into detail, but which I just mentioned, that we strive to be an automatic data-driven policy learning, and that's what we are going to show in some examples in today's lecture. Okay, so just to jog the memory, this is what the memory hierarchy in today's systems mostly looks like. So we have cores, we have individual cores in the processor, and then we have multiple levels of caches inside the cores, which are private to each core, and then we have large last level cache, which is most likely shared across all the cores, and then last level cache talks to the memory controller, which itself talks to the main memory, and then there exists some storage devices which is talking to the main memory also. So we pull the data from the storage device and so on and so forth. So for the sake of today's lecture, what we are going to show is some data-driven applications that we have designed in the past. So one example, we will start with RL-based prefetching mechanism. Then RL stands for the reinforcement learning, and then we will also briefly touch upon a perceptron example, perceptron-based off-chip prediction, which I'm going to be more clear as the lecture progresses. We are also going to briefly show an example of reinforcement learning driven DRAM controller design, and then we'll finally finish with the reinforcement learning based hybrid storage system design. Okay, so that's essentially what we are going to cover in today's lecture. Okay, so let's start with the reinforcement learning based hardware prefetcher. So before going there, so this is the work that we are going to discuss. It's called Pythia, a customizable hardware prefetching framework using online reinforcement learning. We wrote this work, I think, few years back, and it was published in Micro conference in our community. So before going into, how many of you have basic idea of prefetching? Maybe some ideas. Do you know? Okay, I can see a couple of hands. Come on. Okay. So I can see hands from the TAs here. So that's not fair. But okay. So let's just jog the memory. So what prefetching exactly is? So prefetching, as you have also encountered in previous lectures, or like DDCA course or some other courses, that as the name suggests, it's essentially fetching the data before it's needed, right? So hence the term prefetch. So you're going to predict and anticipate that, okay, the program is going to access this data next, so why don't we just fetch it before the program demands it? So that's the whole idea. Why do we want to do this? Because memory latency is high. So if we can prefetch accurately and also early enough, then we can potentially hide the latency of accessing it when the processor demands it, right? So in that way, we can also eliminate compulsory cache misses, like the memory accesses that the processor has not seen before, and you're going to predict it beforehand, and when the processor demands it, it's going to find it in the, hopefully in the faster memory, so that the latency is going to be hidden. Okay, so but then obviously it involves predicting which address is going to be demanded by the processor in the future. So it typically works very well if the program has some predictable address patterns. But like, for example, in this case, you can, so this is I'm giving you some examples of the cache block addresses, right? So in the first case, it's a very strided pattern. You are accessing A plus 1, A plus 2. So it's sequentially you're touching different cache blocks. So you can easily predict that, okay, from A plus 4, you're going to access A plus 5. So that's the whole sense of prediction. In the second case, it's also, it's not exactly same as plus 1 stride, but then there is some predictable strides in between, right? So there is a plus 42 stride going on. So you can also learn from it and then predict accordingly. But as you can see, the more complex we go, then the more unpredictable, or let's say irregular, the program access pattern becomes. And then the problem of prefetching essentially boils down to how to find patterns in such memory access streams, right? So the better you find patterns, the better you can anticipate ahead in time. So judging, so then something that we need to keep in mind, that prefetching does not affect the program's correctness, because if you mispredict some address, it's just simply going to be fetched to the faster on-chip caches. So it's potentially going to have some effects on, let's say, it's going to evict something from the cache, which might be useful. But as far as the program is concerned, your wrong prediction is not going to affect the program, because your program, as long as the program is not demanding it, you're not going to give that data to the program anyway. Okay, but then so there is no state recovery as we have seen. Maybe some of you have seen in the like branch misprediction or value misprediction. It's not, there is no need for the state recovery for this case. So with that said, but then there is some effects of inaccurate prefetching. It's not like everything is like there is no free lunch. So what are the effects of inaccurate prefetching? You waste memory bandwidth. You can potentially waste scarce cache space. You can potentially waste energy also, because you're fetching some data and then you're not essentially using it, and so on and so forth. So we still need to make sure that the prefetch goes accurately as much as possible whenever it's needed, because they may not have the effect in the correctness of the program, but they can have effects on other aspects of the system design itself. Okay, so there is some matrix of prefetcher accuracy, coverage, timeliness, which I'm not going to go too much into detail, but the whole story is that in on top of the accuracy, coverage, and timeliness, we also are interested in bandwidth consumption. That means how much memory bandwidth the prefetching is consuming, as well as cache pollution is these are the two major, let's say, other effects that we should also keep in mind when we are dealing with prefetching. Okay, so how they can be, let's say, detrimental to performance. So this is one example from this paper from feedback directed prefetching. So as you can see that, so we can have multiple various degrees of aggressiveness of a prefetcher, right? So seeing, let's say, a plus 1, a plus 2, you can say that, oh, I have a strided pattern, so why don't I prefetch, let's say, multi lines ahead, right? So I'm going to prefetch a plus 5, 6, 7, 8, 9, 10. Where do I stop? Maybe I can have some sort of let's say aggressiveness defined to me. So as we can see that if we don't do prefetching, so the performance lies over here. So the height of the bar higher is better. On the x-axis you have different workloads, and the y-axis we are plotting instructions per cycle. So as you can see, if you don't do like if you do prefetching, it's giving performance benefit on general, but then aggressive prefetching also gives more performance. The more aggressive you're going, the more performance that you're getting. But that's not actually true for all the workloads. Like there are some workloads, AMPP, APP, LU. So you can see that if you go more aggressive, then your performance actually drops. Why? Because potentially you are using lots of bandwidth. Potentially you are wasting lots of scarce cache space, which the program could have been actually using by itself. So your prefetching is harming those aspects. So the key takeaway from this figure is that in general, aggressive prefetching may or may not work, but then there would be workloads where the aggressiveness can actually hurt performance. Then the question is that, okay, how can we do it dynamically? So there are good ideas on this paper. If you're interested, I'm not going too much into detail, but then you can create some sort of, let's say, decision tree. Think of it in this way. So you can create some sort of decision tree which says that, okay, if I'm going to check some sort of accuracy matrix. If the accuracy is high, then I'm going to check whether the prefetch is late or not, and so on and so forth. You are going to adaptively change the degree or the aggressiveness of the prefetcher accordingly. So the paper shows that if you do this, then you can come up with a dynamic aggressiveness policy that adapts to all the workloads. Like for example, this AMPP and APPLU, which you have seen that the aggressiveness actually hurts performance. There also, if you go for the dynamic aggressiveness, you can extract performance benefit. And in general, they would also be performing better than the aggressive one. Okay. So with that in mind, the question is that, okay, so that's the paper that we are talking about. If you're interested, definitely check out this one. With that in mind, the obvious question is that, okay, we can do a simplistic, let's say, decision tree type structure to make some dynamic predictions on when to throttle, when to go aggressive, and so on and so forth. But can we do better? The answer is yes. So that's the whole motivation behind the paper that we are going to talk. That why don't we methodically formulate prefetching as some form of reinforcement learning? Because you, me, every human being, we are kind of human like reinforcement learning agents, right? So we make some actions, we take some actions, we get some reward from the environment, and we learn adaptively from that reward, right? So that's the adaptivity that we are thinking in this case. So with that said, so that's basics of reinforcement learning. So as I said, like it's an algorithmic approach to learn to take an action in a given situation to maximize a numerical reward. So how many of you have interacted with any form of reinforcement learning before, or have seen reinforcement learning in some aspects? Okay, I can see hands over there. Okay. So maybe you have seen at some point, you have probably heard of reinforcement learning based agent has outperformed many games, like for example, Go as a example that Google demonstrated called AlphaGo. So it's the same ideology in this case also. So you're going to play, and based on the outcome of the game, you're going to get some reinforcement that, okay, whether your decisions were actually correct or not. And game after game, you're going to learn. So that's the whole idea over here also, that the agent stays in the environment, it senses the environment, gets some state. For every state, it's going to take some action. For every action, it's going to get some reward, which reward is essentially going to train the agent that whether this action was correct or wrong. Okay, and the learning essentially boils down to, or one form of reinforcement learning essentially boils down to storing something what we call the Q value. So the Q value, you can think of it as a expected return that you can expect for taking this action in that given state. So the agent often tries to, or let's say more often the agent tries to take that action from that given state, which gives you the highest expected return. But then there is a trade-off between exploration and exploitation also. Like you can easily see that there is a bias here, that if the agent keeps on taking the same action, which is expected to give you the highest reward, then it might not actually see some previously untaken actions, like what could have been happening, right? So for that case, you would also see that there are policies like, let's say, epsilon greedy policies, meaning that with some small probability you are going to take some random actions and we are going to explore the state action space. If that random action becomes better, then eventually you would also incorporate that action into your decision making. Okay, so with that said, we can essentially formulate reinforcement learning, formulate prefetching as a reinforcement learning problem, and it fits very easily. So in this case, the prefetcher essentially acts as the agent, and the prefetcher situated in the processor memory subsystem, which acts as its state. Any feature you can extract from the memory address or memory request that you're seeing to generate this prefetch request can be used as a feature. So one example can be the program counter value. And then you can think of lots of other feature information, which I'm going to show in the next slides. And then for every feature, you're going to take some action, which is the offset here. So how many cache lines ahead from the current cache line you're going to make the prefetch request. So if you're seeing a cache access to the cache line address A, you're essentially making a prefetch request to A plus O. Okay. For this prefetch request, you are going to get a reward. In prefetching case, it's often a delayed reward, meaning you won't get the reward immediately at that point, but then you would get the reward after some point that, oh, whether this prefetch was correct or not. If it was correct, whether was it timely, like was it appeared to the processor before it actually demanded, and so on and so forth. Okay, so we are going to see a example of how it works. Do we have any questions till now? Okay, so that makes me going down to a bit more detail into what exactly is the state. So state, as I said, like it can be a k-dimensional vector of features. You can construct features as many as you like, and each feature in our case is essentially incorporating two pieces of information: control flow, meaning which path of the program the program is executing, and the data flow information also. Right? For example, control flow can be, let's say, program counter value. It can be a branch program counter value. It can be a last 3 program counter value. It's essentially showing that, oh, the program has executed that program that instruction, this, and followed by this. So it's essentially showing you some path of execution the program is taking. Similarly, the data flow example can be, let's say, a cache line address. It can be a physical page number. It can be the delta between last 2 cache line accesses, or it can be, let's say, the delta the last 4 deltas that you have seen. Like the last 4 delta is essentially just as same as last 3 pieces. Instead of showing which path in the control flow the program is taking, the last 4 delta is saying that, oh, you have seen these last 4 deltas to be -1, -1, -1. So that means you're probably going in this direction. So maybe the next delta is going to be something similar. Okay, so that's the state. So what's the action? As I said, like given a demand access to address A, the action is to set the prefetch offset O. So that means you're going to issue a prefetch request to A plus O. Okay, if you have a machine with 4 KB page and 64 byte cache line, you can calculate by yourself. So there would be a huge action space, 127 actions to be specific, in the range of -63 to +63, because you can access a cache line, right? And note that the zero offset is also a valid action. In this case, it means that, oh, the prefetcher is deciding that, okay, I don't want to generate any prefetch request. And then that we are going to see how much impactful that is going to be. Let's say in cases where, let's say, your bandwidth is very much contented and you need to save bandwidth a lot. So that's what it's going to be exercised. And then we can also, and then we have for prune this action space, because the more actions, the more states that we are going to explore, then we are essentially looking at a huge state action space, which is, the bigger the state action space, the higher the time it would take to explore the entire state action space. So that's why we prune it. And then, but then pruning can also come with the problem that, okay, if you prune some actions and then that pruned action essentially became the correct actions that you could have taken, but then you pruned it. So there is always that fear also. Okay. So then comes the most critical component of the reinforcement learning, is the reward structure. So reward essentially defines the objective of Pythia, the prefetcher itself, and it encapsulates at the very least two metrics: the prefetch usefulness, meaning whether the prefetch was accurate or whether it was late, or it was late and accurate both. And it also encapsulates some system level feedback information. What do we mean by system level feedback? Let's say memory bandwidth usage, how much memory bandwidth it consumed. Did it cause cache pollution? Is it, if how much cache pollution it consumed? And you can also think of it all other sorts of system level feedback. For example, let's say energy efficiency. So for example, if you want to design a prefetcher for that works on your laptop, you won't probably work with a similar designing policy as compared to if you're designing a prefetcher for the server processes, right? So energy might be much more constrained for designing a prefetcher for your laptop processes, right? So you can think of all sorts of system level feedback as well into this reward structure. So for the sake of this paper, we have demonstrated it using the memory bandwidth usage, but as I said, like it's general enough to explore all the other types of feedbacks also. So these are the distinct levels, reward levels that I just so we ended up with these distinct reward levels. I'm just going to quickly go through some of it. So for example, let's say this is accurate and timely. So that means the prefetch generated was accurate as well as it was timely. Then accurate and late, it can be, oh, it's actually out of the page that you are looking at, so you cannot do that prefetch. So that's a loss of opportunity, loss of coverage. And then you can also have two different type of rewards for the inaccurate or the no prefetch. So inaccurate and no prefetch, they have the bandwidth usage into consideration. So you can easily think of in this way that, oh, if you have bandwidth available, then you can probably tolerate some sort of inaccuracy, right? Because you have bandwidth, then okay, fine, well, let's go and be more aggressive. But if you don't have bandwidth, then maybe you would like to be, let's say, you would like to, or on the, let's say, conservative side, that if you don't have bandwidth, you would like to go for no prefetching rather than going for inaccurate prefetching, right? But if you have the bandwidth, then maybe you can actually do the opposite. So we're going to show some, like, how exactly, setting these values is going to change the behavior of the prefetcher itself. Okay, the animation is completely broken for some reason. Okay, so as you can see, that if we are providing, let's say, much more higher reward for the accurate values, so it essentially shows that, oh, whenever it can be accurate, it tries to be accurate. And then we are saying accurate plus time, accurate and timely is also getting a much higher reward than the accurate and untimely. So the values that we are setting, it's actually biasing the agent towards taking certain sort of decisions, right? Now, if you change, and then the other thing that you can also see that, oh, if it is inaccurate and the bandwidth usage is also high, that gets the very least reward, because that's the very wrong decision that you would like to make at that situation. So that's how you can, in the paper we have designed, we have described like how exactly that works, and that essentially configures how Pythia should be behaving. But then let's say if you also change the reward in certain way, like for example, so from this figure to this one, we actually we kept the accurate rewards as is, but we increased the reward for the no prefetching on the positive side, but we further decrease the reward for the inaccurate prefetching, both the high bandwidth and the low bandwidth on the further negative side. So what we are essentially showing that, oh, if you are confident and accurate for accuracy, then go for it, right? So that's the pure bias over here. But then if you're not confident, then the agent is literally finding that there is more reward to get if you just simply don't do any prefetching, irrespective of the bandwidth, rather than taking any inaccurate actions. So if you just simply change these reward values on the fly, you would see the objective for the prefetcher itself is changing. So when this sort of objective is needed, so this, let's say you're designing some server class processor, lots of cores accessing on the system, you would eventually you may actually end up going into let's say bandwidth constraint domain. So in that case, you actually need to have some prefetcher which is much more on the conservative side rather than the aggressive side. Okay, and similarly, let's say bandwidth sensitive workloads, like if you're doing large scale graph analytics, like social media graph traversals and so on and so forth, you probably need these sort of benefits. Okay, so eventually we like out of lots of automatic design flows explorations, we ended up using this configuration that we are just mentioning over here. And with that, there are lots of details in the paper. I'm not going to go too much into detail of the actual design, but let me just quickly show you some results from PTI itself. So on the x-axis, you are seeing the number of cores, right? So from 1 core all the way up to 12 core. And the y-axis, we are showing the geomean speed up. So higher is better, essentially. So these are the, okay, animations are completely broken. So these are the prior works that we have been in the literature. And this is what the PTI is performing. So the first takeaway is that across the board, right? So across all the configuration, number of cores that we have thrown at, PTI is definitely improving performance across the board, right? So that's one thing. And the second thing is what also you can see that for 1 core, it was moderately improving performance by 3.4%. But then if you go for 12 cores, it's actually increasing performance more. Why? Because the more the system becomes constrained, the more effect you are going to see from dynamic behavior, like when to stop prefetching, when not to stop prefetching. So that's what PTI is essentially doing over here, and it's getting more performance benefit. So that's what I said. So this is an even more interesting graph. Again, okay. So that's what PTI is, and this is what the other 3 prefetchers are. So on the x-axis, you are seeing different bandwidth. So think of it in this way: the more left you go on the x-axis, the lower the bandwidth is. And these bandwidths are not actually taken out of the hat. So these roughly corroborates to the per core bandwidth of real processors like what we mentioned over here. So this is our baseline, and you would actually have if you use these processors, you are essentially operating at somewhere closer to this bandwidth level. And what you can see easily that these prior prefetchers, so the lower the bandwidth, their performance tanks a lot, right? But then what PTI is showing that, okay, it's still reducing, but it's capping somewhere, right? So it's better, let's say, bandwidth aware as compared to all other prefetchers that we have evaluated. Okay, so that's the number over there. So in highest bandwidth configuration, you can like PTI is outperforming by 3%. In the most constrained environment, like the 100 MTPS, I think, yeah. So that's 17% over there. So that essentially shows that how much bandwidth aware PTI is, and this essentially is coming from the reinforcement learning aspect of PTI. Okay, so if you're interested, definitely check out the source code. It's all available online. So if you're if you want to work on it, if you want to tweak the code, if you want to see how it's implemented, definitely play around with this. So there is lots of other resources out there. And yeah, so that's kind of concludes the PTI paper. Do we have any questions here? Anything? Okay, so if not, then let's quickly jump into some other aspects of and then as I said, like some other form of data-driven architecture. So always the question is, can we do better? So PTI is doing something by managing a dynamic prefetching. Can we do better? So as it stands, that we made this observation that, oh, if you have a very dynamic and adaptive prefetcher like PTI, what happens is that nearly half of the memory requests that were going to the memory, if you don't have PTI, right, they're still going to the memory. So you saved half of them from going to the memory, meaning PTI predicted it, kept it in cache, so that those half won't go to the memory. but still half of them are going, right? So what happens to them? Can we reduce their latency? So that's the whole motivation behind this work, the perceptron-based off-chip load prediction. So let me just quickly discuss this. So this is named as Hermes, accelerating long latency load request via perceptron-based off-chip load prediction. So what's the key problem? So as I said, like these long latency load requests, which are going to the main memory, meaning off-chip, the DRAMs, right? So they are often the most core performance critical request from the performance side. Why? Because they often stall the entirety of the processor by blocking the instruction retirement. Like if your processor gets stalled, then you cannot do anything anymore, right? So that's the whole point. So that's the key limiter of performance. And then we have shown that, okay, there are techniques that we have designed over the time, like sophisticated prefetchers is one technique that you predict ahead and fetch it to the cache so that you don't have to go to the cache when the processor demands it. And then we also do this thing that, we just simply increase the size of the cache. Why? Because if you increase the size, then the anticipation is that, okay, many things would be hitting the cache. Life is good. But then, as I showed, that even if you have a state-of-the-art prefetcher like Pythia at that time, not yet anymore, I guess. So we still see that, okay, 50% of the requests are saved. They don't go to the main memory now, but then the remaining 50% still going. And to make the matter worse, out of this 50%, 70% of them are still blocking the reorder buffer. So that means these dark red part is still very critical to the performance. Can we do something for them? The answer is yes. What we can do. So this is what we found out that, so this is what the on-chip cache access So this is what the access latency timeline looks like for those requests that are still going to off-chip. So you would access L1 cache, you would access L2, then you would access LLC. So they are progressively, getting bigger because the caches are also getting bigger. So you would also incur more time to look up those caches. And then eventually you would understand that, oh, nothing is hitting. So then you would go to the main memory, which is obviously much more bigger than any of these latencies. And then you go out, right? So, but then can we do better? The answer is yes. So if you can anticipate that these requests is anywhere supposed to go out, why don't you access DRAM much earlier than what you could have done? So by doing this, what you can do, you can actually save 40% of the stall by just simply removing the on-chip cache access latency from this critical path. So basically you're broken down into the main memory access. All the latency stays the same, but somehow now the main memory access happens in parallel with the cache accesses so that you ended up saving all of these cycles. Is that clear? So that's a simple, let's say, observation that made us, to go there. But then the question is that you cannot probably access for all of them the main memory. So because that's the key part. Because if you start accessing for all accesses that the processor is generating, and you start accessing DRAM, then you eventually ended up in the wrong side of the benefit, because now your DRAM is now exercised much more than what we could have in the baseline. So the core part of the problem is that you need to know when to access, like which memory request would likely go to DRAM, and that's the part where we would introduce the perceptron predictor. Okay, so that's the goal, that to improve the performance of the processor by removing the on-chip cache access latency from the critical path of off-chip loads. So towards this, we proposed Hermes. Essentially, the idea is, as I mentioned, it predicts which load requests are likely going to go off chip, and for those requests, it would start fetching the data directly from the main memory while also concurrently accessing the cache. Right. So let me give you a quick example. So this is how the latency timeline looks like. Right. So you would see L1, L2, LLC, and then the main memory. At some point, your processor would start stalling. Then at this is the entirety of the processor. When it's stalled, it's a opportunity for performance improvement. But then in Pythia, in Hermes, what we do, so we have a perceptron-based off-chip predictor, which we named as Puppet. So whenever the code generates a request, you inquire Puppet, like, oh, tell me whether it's likely to go off-chip or not. If Puppet says that yes, it would probably go to DRAM, so then you would wait for the L1 data cache access to finish. Why? Because your core likely operates in virtual address. you need to translate in the physical address because your main memory is accessed in a physical address format. So there is a address translation needs to be done, which happens in parallel to data cache access. So that's why we wait for it. Once you know at this point what's your physical address going to be, you can literally start accessing DRAM at that point. So that's what essentially what we do. So Puppet issues a request directly to the main memory controller to start fetching the data from the main memory. At the same time, it's also that request is anyway passing through the cache hierarchy, right? So if your prediction is indeed correct, then the request would eventually arrive at the memory controller, where it would say that, oh, you know what, I have not got back the reply yet, so just wait there. So the moment you would get back the reply, you actually hidden this latency from the path, and then you can just simply send back the data to the core. So that's what happened here. So as a result, what you did is you save these cycles. Maybe your processor is still stalling, but at least it's stalling much less than what it was stalling before. So that's the whole idea. Okay. So with that said, so now let's quickly jump into how the predictor itself is designed. So we designed it at something called a hash perceptron model. So these models are very much powerful, and we have explored, like we meaning the community has extensively explored it for branch predictions perspective, like, oh, what would be the outcome of the branch, whether it's going to be taken or not taken. So we have used similar model for this prediction also. So what this prediction looks like is something as follows. Like, you have some different features that you would be using to make that prediction. For each individual feature, you would have weight table. Okay. So the first thing that we do when we are making a prediction, oh, you have a memory request. Now you need to predict whether this memory request is likely to go off chip DRAM or not. You extracted out all the features. So let's say this is the feature value, and you can have multiple features like this. And then you would use that feature, hash it, use the hash value to index into this table. Each individual table is going to give you some weight values. Okay, so that these are the weights, for example, -4, 12, and -5. So the lowest the value, the lower the value, it says that, okay, it's negatively correlating. That means if this is a feature value, it's definitely not going to go to off chip. If the highest, the higher the values, it's actually positively correlating. That means if this is the value, then it's more likely to be going off chip. Think of it in this way. So once you have all of these weights, you simply sum it up, and after summing, you would have some activation function. Activation is as simple as, let's say, there is some predefined threshold, whether it is higher than that threshold or not. If that's the case, then you would predict that, okay, it would go to off chip. So as you can see, like, this is a very simple form of, let's say, perceptron, single layer, not even multi-layer. You can easily extend it for multi-layer, and you can see performance benefit or accuracy benefit for that also. But this is a simplest form of single layer perceptron network with an activation and making a prediction. Okay, so now the question is that, and all of this is also trained online. So how exactly we want to train this thing, or how exactly we can train this thing? So we would train it as follows. So let's say you predicted that, okay, this request would go to off chip, but in reality it did not go off chip, right? So you need to now update the weights in certain way. How would you update? So that means you predicted off chip, meaning the activation happened, but it should not actually happen. So that means you got the value, some of the weights to be 3, which is higher than the threshold. It should be lower than the threshold, right? So you just simply backtracking, right? So what we do for stochastic gradient descent for going back and back propagation is the same form of back propagation happening in single layer perceptron. So activation shouldn't have happened. So that means your sum of weights should be lower than the activation threshold. So that means all individual weights should be lower. So what you do, you would again extract the feature, and you would hash all the individual weight table, and you would just simply decrement the counter. So all of these counters are essentially integer values that ranges from, I think, -16 to +15. So that's like 5-bit values. And you would just simply do either increment and a decrement, and then it works. But you can easily, as you can see, that you can easily extend this thing for multi-layer, floating point values, and so on and so forth. Okay, maybe I'll just take a couple of minutes to finish this, and then we can take the break. So we evaluated this idea on lots of single core memory intensive traces, as well as 8-core memory 8-core traces also. And we evaluated based on, like, compared against different types of prefetchers, because clearly this idea is also synergistic to prefetching, right? And then there are some walks that we can either model it as a off-chip predictor also. So we compared against them. And then there is an ideal off-chip predictor, meaning that, oh, you have a perfectly correct prediction, right? You know that, okay, it's going to be this. What happens in that case? So we did that. And so I'm going to skip this. So yeah, so this is what the performance number looks like. So this is what Hermes provides. So Hermes provides 11.5% performance benefit, where Pythia itself is providing 20.3. So as you can see, like Hermes is not by itself is not that aggressive or not that powerful also. So, but the benefit is that it actually provides more than 50% of the performance by having only 1/5 of the overhead. Like the big structures that we have for Pythia, like we only have 1/5 of the bigger structures like this. So literally you can see that there is a trade-off here. You already saw. But then the beauty is that if you add Hermes and Pythia together, so that means off-chip prediction is also going on and prefetching is also going on. And this is a naive integration. So then you can see that, okay, there is performance benefit to have on top of Pythia. So that means whatever Pythia is covering, you are already fetching. Something that is not covered, then they would be short-circuited by Hermes, what we just showed. And then we also showed that, if you have an idealistic predictor, it's also very close to that idealistic performance itself. And we did some studies with let's say bandwidth event policies, like for example, so this is, and these are even more workloads. So that's why you would see for, in this case, Pythia is actually, the more workloads you would throw, you would see that, okay, it might actually go down also. But what the key aspect of this figure is that Hermes might not give you the same performance benefit, but it's when the system starts becoming much more constrained, that same policy actually starts giving better performance than prefetcher. So think of it in this way. So prefetcher is a policy which is like you aim big, you miss big, and Hermes is like you aim small and you miss small. So you aim small, that's why you're getting small benefits as compared to Pythia when the system is very happy and you have lots of resources available. But then if you go to the negative resource part, then it starts providing performance benefit even more. And if you have both of these together, then it provides something. But then the key aspect that you can see here, that this black line, which is the Pythia and Hermes, is literal copy of Pythia itself. So, and it's also going down here, right? So one thing that you can easily understand, that even though there is a dichotomy of behavior at this inflection point, the naive integration of Pythia and Hermes is not actually following the best of both. Because if it is best of both, then it would have been somewhere here, right? So it's clearly definite not going for orchestrating both of these components together. So there are definitely avenues to orchestrate these things much more better in most likely in constraint systems. Okay, so there are lots of other examples also and results. So as I said, like just to summarize everything, so we advocated for off-chip load prediction. It's a fundamentally different form of speculation than load address prediction, what prefetchers do. So you predict the address, but instead of now predicting address, you are actually predicting a single bit value, whether this memory request would go off chip or not. Okay, and we just showed that, okay, it can be applied by itself, or it can be combined with load address prediction, like prefetching, to provide additive performance benefit. And we show that, okay, it has decently high accuracy, but it's not too much high also. It's 77% high coverage. So ML folks, you can think of accuracy as precision, and this one as recall. So it's not there. You can improve it further. And if you want to improve it, definitely check out the GitHub. It's everything is online again. And the way that we have written these codes, like there is some sort of base predictor, and so you can just simply extend it. You can write whatever train function, whatever predict function you want to use, like go wild. Like you can just simply see that you would get this sort of results out of the box. That, oh, your precision is this, recall is this. You can just simply start tuning it even more, and you would see performance benefit from that. Okay, so with that said, so that's the end of the second part. And before going to the DRAM controller, I think let's take a break, and then we can come back when the bell rings. Thanks. Okay, so welcome back again. So till we have covered two policies, a bit different in terms of the learning mechanisms that we use. One is reinforcement learning, another was perceptron. Both of them are online and online trained, online making decisions online also. So we're going to take we'll go a bit farther away from the code, and then we'll see the applications of reinforcement learning to be specific, even in more part of the hierarchy now. But before going there, do we have any questions till what we covered? Anything that you did not understand? Any burning things? Okay, so if not, then let's go to the third part of the today's discussion, is reinforcement learning based DRAM controller design. Okay, so let me just get rid of this thing. Okay, yeah. So what are the what exactly is DRAM controller? So DRAM controller is the key component of the system which essentially talks to the DRAM, right? So and when you are going to talk to DRAM, lots of constraints that the DRAM controller needs to ensure for the correct operation of DRAM. So if you don't ensure these constraints, then essentially your DRAM accesses might be returning wrong data that you have actually put it in it. Okay, so exactly. So this is what the function of the DRAM controller looks like. So it services the DRAM request that's coming from the different cores, while obeying also DRAM timing constraints of the DRAM chip that you have already installed. So constraints meaning what? Constraint can be coming from lots of different aspects, like resource conflicts, like for example, bank conflict, bus conflict, channel conflicts. DRAM controller needs to keep track of everything. So if two requests are going to the same bank, they cannot go together. If two requests are going to the same channel, they need to obey some timings, so on and so forth. And then they also need to keep track of minimum read to write to read delays, and then so many timing parameters that I'm going to come quickly to the next slides. So it essentially translates each memory request that's arriving to the DRAM controller to something what we call a DRAM command sequence. Like DRAM command sequence is something similar to, let's say, I'm going to show some examples. So let's say you want to access this cache line, but you don't, the DRAM controller knows that, okay, where exactly in the DRAM physically that cache line content resides. So it would simply convert the address that you are providing. It would create something what we call the DRAM commands to access the DRAMs with specific timing parameters, and to ensure that you get the data, the correct data that should be there. Okay, and it also buffers and schedules requests that all the cores are giving for high performance as well as quality of service. And so it reorders the request, and then it also takes care into let's say row buffer hits, which bank that you are accessing, which rank, boss management, and so on and so forth. So let me it's also manage the power consumptions and thermal envelope of DRAM. So turning on and off DRAM chips whenever it's needed, and then switching different power modes in DRAM, and so on and so forth. Okay, so this is exactly how the DRAM controller looks like. So inside this controller, you have different queues, right? And then they are interfaced with the actual DRAM chip, and then you would have some sort of the signaling interface, and then all sorts of CPU and IO device, they put their request into this request streams. There is some sort of arbiter which essentially reorders the request, which request to go forward, which request to go later, and so on and so forth. We are going to show examples of it, how it does this, and then it puts into the queue, and then eventually every queue gets channeled to the DRAM actual device. Okay, and then just to jog the memory, so this is how the DRAM bank operation looks like. So DRAMs are essentially organized in let's recall from a couple of lectures back. It's essentially organized in some columns and rows, and then you have something called row buffer, which and then all the so when you read one row, the entirety of the row gets copied to the row buffer, and then you read the data from the row buffer one by one. So for example, let's say we are accessing row 0, column 0. So then what we do, we put the row address 0 to the row decoder. It would select the row 0, and then once it gets selected, then it would be copying to the row buffer. So then the row 0 comes to the row buffer. This is what we call the open row. Now you would also say that, oh, I need column 0. So then from the row 0, you would get the column 0. That column data would be sent back to the processor. Now then, let's say if you get the next request coming to to the same row but to a different column, what happens? Then it would say that, okay, row 0. Then it would already see that, okay, the row 0 is already open. So that's what we call a row buffer hit. So that means you don't have to open this row anymore. So that saves latency. We are going to show like this is the row buffer hit latency is much lower than the row buffer miss latency. And then you said, oh, I need column address 1. So then I'm reading 1, sending it to processor. Similarly, if you access column at 85, again row buffer hit, you access column 85, send it to processor. But now let's say you're accessing row 1, column 0. What happens? The row 0 is already open. You need to close this thing. So this is what we call a row buffer conflict. You need to close this row. And this operation, keep this in mind, this operation is not something that DRAM does automatically. It's the responsibility of the DRAM controller to keep track of what's actually happening in the DRAM. So that means when there is a row buffer conflict, it needs to send that command. That thing would be, this is what we call a pre-charge. It would be first taken back to the actual row, and then the new row would be opened, so which is row address 1. Row address 1 would be copied here, and then column address 0 would be probed here, and then it would return back the data. So as you can easily anticipate, like if everything, and all of these copies, like how much time you need to wait when after this, after you inject this command that, oh, copy this row, after that command, open the row, how much time you have to wait for making the first access. If it is a row buffer hit, then how much time you have to wait since the previous access to access the next, let's say, entry or any entry in the open row. And if this is a row buffer miss, then or row buffer conflict, then you have to put it back and then open it again. All of these events has their own internal timing dependencies. Like you need to maintain this much of time to ensure correct operation. If you violate the time, the DRAM manufacturer is not guarantee you. They are not guaranteeing you to get the correct data that you have put in the DRAM. Okay, so everything essentially falls down to the shoulder of DRAM controller, and then so as we said, like so this is what this part of the core of the DRAM controller looks like. So let me go back quickly. Yeah, so this part of the controller looks like that. You need to, once it goes to the arbiter, and then it selects which request you need to do, and then it will generate the DRAM sequence, DRAM commands, and it would put it over here. Okay, but then the question is that, okay, how exactly when we have the request queue, which request we want to select first, like which one to prioritize and which one not to prioritize. So the prioritization, it can be actually based on multiple aspects, right? So we can say that, oh, the oldest entry or the oldest request needs to be prioritized first. That's the obvious option. Then you can also say that, okay, no, I'm not going to always say that, okay, first come, first serve, but then I'm going to say, oh, first come, first serve, but we are also going to prioritize if there is a row, open row, if there is a row buffer hit. So then we call it first row, first come, first serve, FRF-CFS, right? So, and then you can literally think of lots of other features that can also be taken into account when you're making this prioritization decision. Like, for example, oh, is this request a prefetch request, or is this request is something that the core actually demands, right? Depending on that, you may want to prioritize, let's say, the request that the processor actually demands rather than the prefetcher is generating by itself. Maybe the prefetcher is generating something wrong, right? So you can you think of it in this way. Requester type, is it a load miss? Is it a store miss? Request criticality, meaning the memory request that's generating, the memory instruction that's generating this memory request, where exactly that memory instruction is in the core. Like, for example, is it very close to the head of the reorder buffer that, oh, if you don't prioritize this request, it's quickly become the oldest instruction in the processor, and then it will start stalling everything else, right? So lots of features that you can think of that would be important to make this decision. And just like as if life was not hard, then you also need to obey all the timing constraints that I just mentioned. Like there are lots, like literally 50 plus timing constraints that you have to keep in mind when you are when your DRAM controller is actually making all those DRAM commands. And this is one quick good technical report that you can go for to understand how many DRAM parameters are like timing parameters are there. Like there are lots of other timing parameters mentioned in these papers also. Like these are some that we are showing over here, but then it can go pretty complex very quickly. So what's the reality? The reality is that it literally very difficult to design a policy that prioritization policy that maximizes performance, but not only performance but also quality of service, energy efficiency, and so on and so forth. Why? Because too many things to care about. But then what's the dream? The dream is obviously like we were being lazy. Wouldn't be nice that okay, if we can, let's say, throw this entire complexity to some sort of let's say methodical way of modeling, and then we can say that okay, DRAM controller is automatically going to schedule finding a good policy of its own, right? So that's the whole idea. That idea kind of motivated for Pythia. This idea also motivated for this work. And keep this in mind, this work is 2008. So it's one of the first work that explores reinforcement learning in let's say computer architecture or designing systems domain. So yeah. So with that said, so that's the whole motivation behind the self-optimizing DRAM controller. So as I said, like problem is that these DRAM controllers are very difficult to design, and it's like for a human designer to keep track of everything, all the timing parameters as well as the features that which type of request is it critical, is it not critical, to keep in mind, and it's very difficult to come up with a holistic solution over there. So the idea is that the memory controller that adapts its scheduling policy to the workload behavior as well as system level feedback and conditions using machine learning would be much better to design automatically, right? So that's the observation, as I like kind of alluded to. The reinforcement learning in this case maps very nicely to the memory controller policy design. And what we are going to do is essentially we are going to design the memory controller as a reinforcement learning agent. So I'm essentially showing the same figure that we showed in Pythia. So agent stays in environment, takes actions, gets reward, sends the states, so on and so forth, right? So what happens in this case for the DRAM controller? So the scheduler, the DRAM like the scheduler inside the DRAM controller is essentially acts as the DRAM agent, and the entire memory subsystem acts as the system where the environment where it resides, and then it's going to schedule some command, so which is the action. For every command, it's going to get some sort of reward, which is essentially measured as the data bus utilization. So I'm going to discuss what exactly that is, and then also it's going to take some state attributes into consideration. What which features you want to look for when you're making this decision. So that's that. So that's the paper that we are discussing here, self-optimizing memory controller or reinforcement learning approach. So what they do is that you have the transaction queue inside the DRAM controller. So every transaction queue has this information, like which bank it goes, which row, which column it's accessing, what's the data, blah, blah, blah. And then from this transaction queue, you are going to extract the state information. That state information is you're going to provide it to the scheduler. The scheduler is going to take the actions accordingly. The action is essentially going to generate, okay, which request to prioritize now. And based on that, you're going to generate the command. And you will go, like once you send the command, you would send the address, both this goes, and then you would get the data back. And when you're like in this transactions, like when the transaction is going on, we are also getting track of the reward. So what the reward is, and that's the most fundamental pillar of reinforcement learning. So reward in this case is as simple as, let's say, +1 when you are actually scheduling some read and write commands to the bus. So that means your bus is utilized, and 0 all the time. So that means if you have not scheduled anything, you decided not to do something. So that's what the 0 is. So that means if you want to increase the reward as much as possible, it essentially means that the goal that we are providing to the controller is to maximize the long-term data bus utilization. So as long as the data bus stays utilized, the more reward it's going to get, right? But you can think of it, scheduling the, you can think of it, the reward in many other aspects, right? So this is one way of formulating the problem, but this is not only way of formulating the problem. So you can think of it, let's say, oh, if this is performance heavy, like you are solely going for maximizing data bus utilization. But that also means that, okay, you have lots of cores running in parallel, and the DRAM controller just simply say that, okay, I want to increase the long-term data bus utilization, and I'm just simply selecting the request from one core only. So it kind of like naturally you can see that it has no quality of service metric into consideration, right? So what's the guarantee that it's going to be fair across all the cores that you have running in parallel? So you can think of it, this reward function is as even more sophisticated way. So it is not going to be just only one, let's say, single prong attack, but you can literally think of it as a multi-dimensional reward, right? So you're not only going to optimize for performance, but maybe for quality of service, maybe for fairness, right? So you can do this. Then the state attributes, as it stands, there we have like 3 types of state attributes: the number of reads, writes, and the load misses in the transaction queue. That's one way, that's one information. Number of pending writes and the ROB heads waiting for the reference flow, like how many so ROB heads in the sense like these let's say DRAM commands are very much critical, because you need to make them you need to process them as fast as possible, because they are on the oldest entry of the reorder buffer. So the processor is literally waiting on them, it cannot do anything. And then the request relative order to the in the reorder buffer. So that's again like how far it is from the head of the reorder buffer. So that means it gives you some sort of priority metric or criticality metric. And then the actions that you can take is essentially all the possible, let's say, DRAM commands that you can think of: activate, write, then read either load maze, read store maze, pre-charge pending, pre-charge preemptive, and no operations one. Like just like we have 0 prefetch delta in Pythia, we also have a no op that it decides not to issue anything. So this is the performance result in nutshell. So as you can see that so what are the options here? So this is the in order. So that means you're literally servicing all the requests in first come first serve. Then you have the open row, like first row policy. Like if you're going to go for the row buffer hits, that if you see some request in the queue which is going to the same row that is already open, then you would prioritize them first. If there isn't any, then you would go for first come first serve. So that's this one. Granted that this is not probably the best, obviously this is not the best in today's time. Then you have the reinforcement learning based agent, which we just mentioned, and then we can have a headroom policy, which is the optimistic, like you manually so you like which one to select, which request to prioritize to maximize the bus utilization. So that's, let's say, you can think of it as a headroom. So as you can see, the numbers are normalized to the first to first come first serve policy, and the reinforcement learning based policy is providing 19% performance improvement. Obviously the in order policy is performing worse than the first come like FRF CFS policy, but then you can also see that you literally have 70% of headroom. So you can see that the 2/7 of the headroom is bridged, but then there is also a lot of gap to be bridged for, right? So if you want to go and take a jab at it by yourself, definitely this is one of the key aspects of the system design that you can still make some impact on. Okay, so what are the benefits of the optimizing DRAM controller? As I said, like it's continuously learning in presence of changing environment. If the workload changes, if the workload's access pattern changes, if the system's behavior changes, it would continuously learn from them. It reduces the designer burden, so for finding a good policy. So the designer only needs to specify that what system variables might be useful to look for and what's the reward structure. So essentially what target to optimize. But they are not going to say how to optimize. That how part is going to be automatically detected by the reinforcement learning's own policy. But then like nothing is free lunch also. What seems to be much easier, it's also not going to be easier in the real life. Like how exactly we want to specify the objectives, right? So because the objectives, the way that we are going to define the reward structure, essentially the agent is going to make that same actions. Like we saw in Pythia, that if you change the reward levels, it's going to interact differently with the different objectives. So similarly, as I mentioned, that in this case, what we in this paper, what they mentioned is purely performance. But then, is this the only thing that you need to care about? Probably not. You can incorporate fairness, you can incorporate quality of service, and so on and so forth. And then there are also there is a question about the hardware complexity, like how much hardware it would need for storing all those Q values and so on and so forth. And most importantly, it's a design mindset, like, oh, if it is working in this way, why make it complex, right? So that's something that we always need to come out of. Yes. Okay, so if you're interested, definitely go check take a look at this paper. And then this paper is one of the paper that was selected for a retrospective in a couple of years back in ISCA, when they celebrated the 50th anniversary of ISCA, which is the flagship conference in our domain. So that's the retrospective also, because it was, I would say, much ahead of its time, and now we are kind of catching up when we have started understanding the impact of reinforcement learning in multiple other aspects of the design. So yeah. So with that said, I would hand it over to Rakesh. So Rakesh is going to give you another example of reinforcement learning in hybrid storage system. So which is you would probably find it interesting. Thank you, everyone.
Thanks, Rahul. Okay, so what we are looking now is how we can use reinforcement learning in storage. And the problem that we are trying to solve in this paper is, so you, in any computing system, you have multiple storage disks where you store a lot of data. And these days, with a lot of data intensive applications, you need to store some of the data sets in the storage system. So how do we decide which data needs to be placed in the faster device, which data needs to be placed in the slower device? If you have multiple such disks, then it's a very hard challenge to solve with fixed policies or hand-tuned policies. So this work basically looks at how we can leverage reinforcement learning for data placement in hybrid storage systems. So what this work was presented in ISCA 2022. So what I'm going to present is how prior data placement techniques have some limitations, and how do we formulate data placement as reinforcement learning problem, and then the design of Sybil, which is the name of this work, and then we show some key results and conclude. So what is a hybrid storage system? So we have multiple disks. Here we show a fast device, which is an Intel Optane disk, and then a slow device, which is a hard disk drive that is kind of going off from the systems now. So you have a storage management layer, which basically
exposes the logical address space of these storage devices to the applications. So the applications can read and write into these disks. So when the applications perform reads and writes, it basically decides which of these devices the data has to go into. And it also performs promotion and eviction, which is basically moving the data when required between these devices. So with that, so the performance of hybrid storage system highly depends on the ability of the storage management layer to manage these different workloads and these devices. So so to motivate this, the use of reinforcement learning, we looked at two key shortcomings of prior approaches that perform data placement. So what we observe is that these prior approaches lack the adaptivity to changes in the workload. And if you change the device configuration or add more devices, then these policies are not able to adapt to these changes. And then the second limitation is that these policies lack the extensibility to more devices. So if you add from 2 devices, you have 3 devices, you add one more device, then it basically the policy fails. So to just give an example of what we observed in these prior approaches, we show a heuristic based approach called CDE and an RNN HSS policy, which is based on supervised learning approach, which requires frequent retraining. So what we show here is average request latency. So the lower the bar, the better it is. So if you look at CDE, the performance against an Oracle policy, which is our let's say the ideal policy that knows all the access patterns to make a decision. So here you can see in one of the workloads, CDE is performing pretty close to the Oracle policy, but the same policy, when you run it on a different workload, there is a large gap in the performance. So the same applies to RN and HSS as well. So this is one scenario where if the workload changes, the policy is not able to adapt to these changes in workload characteristics. Then we look at changes in device types and configurations. So these policies don't really adapt, consider the underlying storage device characteristics like the latencies of the new device that gets added, or there are different operations that are being performed within the devices like garbage collection and so on. So here what we observed is that if you have a policy like CDE, it basically performs worse than a slow only policy, which is basically if you put all the data in a slow device in your hybrid storage system, that's the performance we are looking at here. And CDE is still not able to perform as well as slow only. But when you change the configuration, the CDE policy performs better. So if you change the configuration, the policy is not able to adapt well to the changes. So that's the other limitation that we look at. The third limitation is basically the lack of extensibility. So these policies are so rigid that they are hand tuned and basically consider the number of devices that are being that are present in the system. So when you have 2 devices, the designer has to hand tune the policy. But when you add an additional device, then the whole policy has to be changed on where to place the data when the access pattern is of a particular type, and when the access pattern changes, you need to place it in another device. So this is a challenge that designers always look at. So the goal of this work is to basically design a data placement mechanism that has both adaptivity for different workload changes and different types of device characteristics, and also can be easily extended to multiple devices. So to this end, we propose Sybil, which uses reinforcement learning to perform data placement in hybrid storage systems. And so I'll just give a brief description of or idea of how we formulate data placement as an RL problem. And some of this you have already seen in the previous ideas that Rahul has presented. So I don't want to go into the basics of reinforcement learning again. So so what is the how do we formulate our data placement as an RL problem here? So we have an agent that is Sybil in our case. What is the environment? We have the hybrid storage system, and the agent learns from the environment. So it basically looks at the features of the current request. We'll go into what are these features, and then also the system. And then it makes a decision on where the data or the current page has to be placed, which storage device, whether it's the fast one or the slow one. And then it gets a reward from the environment, which is basically using the request latency to provide a reward to the agent. So what is the state feature? What is the state that we use in this work? So basically, we have a 6-dimensional vector of state features, which looks at characteristics of the application and also the system. So we have the size of the request that is coming from the application. We have the type of the request, whether it's a read or a write. Then we have the access interval. We have the access frequency, and we look at the capacity of each device in the system, and also the where the data is currently placed. So if we consider more of these state features, then we also make an informed decision, but then there is a trade-off. So you need to also manage the storage overhead for having all these state features. So we basically quantize the state representation into different bins. So we classify them into number of bins, and we lose some accuracy with that, but we also reduce the storage overhead. Now, let's look at what is the reward. So the reward is basically the objective of the RL agent. And in our case, the reward is formulated using the request latency. So whenever the agent places the data in one of the storage devices, the request latency or the latency of the request is basically provided as a reward to the RL agent. And why we use the request latency is because we want to optimize for performance. And request latency also captures the internal state of the device. So if there is garbage collection going on, or if there are queuing delays within the device, then then latency can capture that. It can also capture the throughput of the system and then the evictions. So if there is data movement happening between the devices, then that also gets captured as a latency overhead. So we provide more details in the paper, and I would point you to that. Then what is the action? Action is pretty simple. We basically look at which storage device the data has to go into. And for every new page that comes from the application, we basically select the storage device. And this is a simple action, and it can be easily extended to number of storage devices. And there are also other kind of sub actions that we look at. So there is also eviction happening. So if let's say Sybil places all the data in the fast device, because it's a very hot, the application is frequently accessing the data, then it has to evict some page, evict the page from the fast device at some point because it reaches its full capacity. So that is also happening with Sybil. And then whenever the application provides an update from its end, it also promotes the page from one device to another. So that's basically the action of Sybil. Now we look at the design of Sybil. So unlike some of the techniques that Rahul has already presented, this is something that is implemented in the software layer. So as you can see, it's something that we implement in the kernel space of the operating system. And here we have let's say the space or the flexibility to use a neural network compared to a queue table that we have seen in some of the prior works. So here we basically have two separate threads. One is called a decision thread, which makes the decision on from when the request comes from from the application. And then it basically says, okay, the data has to be placed in the fast device or the slow device now. There is also a training thread, which basically looks at all these requests from the requests and the environment also, and then basically trains the neural network using all this data. And then it frequently updates the weights of the neural network in the decision thread to keep the so that the neural network can adapt to the changes in the workload. So there is some asynchronous execution that is happening in the system. So this is the design of Sybil. So we have a decision thread where we have a inference network, and then there is a training network in the training thread. So these two networks are identical, and they are simple feed-forward network, which means that every node in the neural network is basically connected to the other to every other node in the next layer. So when the storage request comes from the system, so we basically capture all the features that we need from the request, and then we create something called an observation vector, and that is the state feature that we provide into the inference network. And the policy of Sybil is to maximize the reward that it gets in the long term. So it basically picks the Q value that has the highest Q value, and then the state and the action that the agent makes, and then the reward that it gets from the hybrid storage system is collected as an experience and stored in an experience buffer. So this is a buffer that basically stores experiences from different requests, and then this experience buffer basically feeds data to the training data set to the training network. So what is happening is that we are trying to reduce the load on the IO request when it comes, so that we make the decisions very fast, but the training network is running in the background to basically adapt to different workload scenarios and environment changes. So I've already described this. So there is also a periodic policy weight update happening. So let's say every 500 requests or 1,000 requests, we basically transfer the weights of the from the training network to the inference network, so that the inference network is also kind of catching up with all the changes that is happening. So that's basically a quick description of the RL agent and Sybil. Now we look at some evaluation. So any questions so far? I don't know how we are doing on time. We have 10 minutes. Okay, so I'll quickly go with some results. So we basically evaluate this RL agent in a real system. So we basically built a hybrid storage system with different disks. So we have the fast SSD here, then a bunch of slower SSDs, and then the slowest hard disk drive, which is also there in the system. We use a desktop class processor for our inference, and we have multiple configurations. So a cost-oriented HSS configuration where we have the high-end SSD and a low-end hard disk drive, and we have a performance configuration where the latencies are quite comparable. So we evaluate this the Sybil and prior policies on 18 different workloads from MSR Cambridge and FileBench suites, and then we also implement 4 different policies, prior policies. 2 of them are heuristic based, which means they're hand tuned, and 2 of them are learning based, which basically they are supervised learning approaches, which use labeled data for training, and they need frequent retraining. So in the cost oriented HSS configuration, so you see the results for different workloads, and on the y-axis we are seeing the average request latency. So the lower the bar, it is better. So here we look at Sybil in pink, and basically Sybil is able to perform as close to the Oracle as possible, and it performs better than all the prior approaches. So in the performance oriented HSS configuration, so we again see that Sybil is able to provide up to 21.6 or on an average 21.6% performance improvement, and this is because it dynamically adapts to the its data placement policy to all the changes in the workload. Now Sybil is also so the reference that we have is an Oracle policy, which basically knows all the future access patterns, and it makes a decision based on that. So when we compare Sybil to an Oracle policy, it actually achieves 80% of the performance of an Oracle policy. So Then extensibility is another factor that we looked into, and Sybil is basically, it's very easy in Sybil to add a new action if you add a new device. And then the only feature that you need to add is basically the remaining capacity of the new device. So when we compare, so we actually had to redesign, take a heuristic approach, and then basically extend it to a tri-hybrid HSS configuration. So here we look at the performance of Sybil, and we see that Sybil is able to consistently outperform the prior approach, and its performance has actually improved compared to a dual HSS configuration. And it actually provides ease of extensibility because you just need to add a few things in the neural network, and then you can basically run it for different configurations. In terms of overhead, we have around minimal overhead in terms of storage cost. We have it consumes around 125 kilobytes. This is mostly for the experience buffer and the inference and the training networks. And we also take around, Sybil also takes around 40 bits for storing the metadata, so that we use the features that we use for training the network. So that is consuming around 40 bits. And the inference and the training latencies are very small because we have some, because we are looking at a storage system, the latencies are in the order of microseconds and not in nanoseconds like the DRAM or the cache subsystems. So the latency is quite acceptable in a storage system. We have more evaluation in the paper. We also evaluate the throughput of the system. We show how Sybil can outperform prior policies in unseen workloads. So you basically train Sybil on a particular workload, but then deploy it on another workload which Sybil has not seen. And Sybil is able to perform better in those scenarios as well. In terms of mixed workloads where you have multiple workloads running in parallel, it can also capture those changes very well. We also show some sensitivity analysis in terms of different, like what is the feature selection we did, different hyperparameter values. And then the important part is, like, we also try to explain the decisions of the RL agent, which is typically a black box at this point. So explainability of the RL agent's decisions is a key for works in this area. So this is the archive link to the paper, and we also open source the code of Sybil, so you can take the code and then use it in your systems as well. So in conclusion, so Sybil is the first RL-based data placement technique in hybrid storage systems that provides adaptivity, extensibility, and also ease of design and implementation. We evaluate Sybil on real systems with many different workloads. Sybil improves performance by 21.6% compared to the prior approaches. And on a tri-hybrid system, which has 3 devices, it even performs better. And it achieves 80% of the performance of an Oracle. So that's Sybil. But I have another slide which basically gives some kind of major directions in this area. So Sybil basically looks at data placement, and it tries to optimize the performance of data placement. So what other objectives can we look at? So here in a storage system, we also need to look at energy consumption. So basically, we can look at the energy consumption of the storage devices and add that as another objective that we can optimize. Then endurance is another key factor that we need to look at. So storage devices have limited endurance because of the underlying architecture. So we need to also look at endurance for optimizing. So in Sybil, we looked at a reward structure which basically looks at latency, and it performs, and latency translates to performance improvement. But we also need to take design reward structures which are more accommodative of other optimization objectives also. Now, so what we did not discuss is basically the other tasks that the storage system performs, which is basically data. We looked at data placement, but data migration is another thing that the storage system performs, and that needs to be also adaptive to improve the overall performance of the system. And then we also look at we need to also look at other heterogeneous memory systems like DRAM plus NVM or even CPU caches plus DRAM. So these kind of other heterogeneous architectures can also benefit from reinforcement learning. But there are challenges there, and latency constraints in terms of inference and training needs to be looked at while designing RL models for that. So with that, I'll close Sybil here. I think we have another slide. So Rahul, do you want to do it? So to summarize, the challenge and the opportunity for future is there's a lot of potential to build self-optimizing computing architectures which are data driven. We have a lot of data being generated in applications right now. So basically all these systems have to learn from the data and then change its policies to have a better computing architecture. So with that, this is the inspiration from human brain. So with that, we'll close the lecture for today. Thank you.